Looking at equilibrium again. So assume that gaseous hydrogen iodide is synthesized. This is a vocabulary term that you need to be familiar with. What does synthesized mean? Made, produced, created, whatever. So as soon as it says is synthesized, what does that tell you about hydrogen iodide? It is a product. Very good, Charles. So we need to make sure that whenever we write our rice table, that we have that as the product. So I'm going to go ahead and set up our rice table. So I've got R, I, C, E, X, on, and E, F. So already I know that hydrogen iodide is my product. What is the chemical compound for hydrogen iodide? HI. Hi. Okay. Hydrogen iodide is synthesized from, and these are the two other things. It says hydrogen gas and iodine vapor. I want you to go ahead and finish the balance reaction. Go ahead and finish your R row for me in your rice table. Finish your R. What? Honestly, not much. Or yeah, you did miss a lot. Did y'all miss the whole K versus Q thing? Then yeah, you missed a lot. Nope. How many of you missed the diatomics? Good. Don't do that. Now, is it not balanced? Very good. I need to put it in front of HI. So now it's our balanced reaction. We cool with this idea? Now, there's something else that I want to point out, and it's how they worded something. It says hydrogen gas and iodine vapor. In terms of the molecular structure, is there any difference between hydrogen gas and iodine vapor? No. Why? Because technically they're both what? Gases. But why in the world would they say, hey, this is a gas and this is a vapor? Why would they differentiate? What is the definition of a vapor? Something that is a gas that's normally not a gas. Now, we don't have a periodic table hanging up in here. However, iodine has turned into a gas, but it's normally not a gas. If we were to be able to see a periodic table, what would iodine be? It is a solid. I promise. If you look down the halogen row, what is the very top halogen? Fluorine, and it's red. Why? It's a gas at room temperature. What is chlorine at room temperature? A gas. That's why it's red. What is bromine at room temperature? It is blue, which means it's what? A liquid. And what is iodine? It is black because it is a solid. So all within one row, we have three different states of matter. That's why it says iodine vapor, because normally it's a what? Solid. So what does that tell us about iodine in terms of it being a vapor? How did it get to be a vapor? It heated up. Someone said it. What is the process? Don't say it out loud. Hang on. What is it? Don't say it out loud now. When something goes straight from a solid to a gas, how many of you know what the name of that process is? What is it, Coleman? Sublimation. Okay? That is the process of solid to a gas. Was that a quiz ball question? Did you get it right? Did you get the point for it? Okay, good. Just making sure. Don't let anyone beat you to the punch. So, it says iodine vapor at temperature where the equilibrium constant is. Now, let's talk about this. Is this a good way to write the equilibrium constant? No, that's a really stupid way. What is that real value? It is 100. So, K is equal to 100. I'm actually going to make this a little smaller. K is equal to 100. Suppose HI is 5.00 times 110 to the negative first. Are you kidding me? Seriously? Did they really write it like that? We don't want that. Let's change that. What would we change that to? 0.50000. You're right, it was unnecessary. However, if I stick with significant figures, actually there's one too many zeros. Yep, I did one too many, sorry. I almost screwed it up. That's technically how it should have been written, to 4 significant figures. This is the important thing. We've talked about the number. Soon as you see that, what does that tell you? It is KP. Now, do we have a reaction that you can use? Please write your KP for this reaction. Write your KP for this reaction, please. Again, practice makes perfect. You have the balanced equation right there. Write your KP for it. Know what you got? Very good. Okay. Don't mess up the K's. Now, somebody told me in second period, Renee, when she does it, does she do the parentheses? No, but what does she at least do? She definitely does the P's. I personally like the parentheses because it organizes a little bit better. It makes you mentally understand what's going on. It separates everything out for you. So again, as long as you had the P's, you're cool. But you can't just have the parentheses. So we have our KP. So now let's continue reading. It says, suppose HI at 0.5 ATMs, H2 at 1 times 10 to the negative second. Let's change that. What will we change that to? 0.01 ATMs. And I at 5 to the negative third, what will we change that to? Very good, 0.005. ATMs are mixed in a 5-liter container. So do you agree that all 3 of these things are mixed in the very beginning? They're all mixed together in the very beginning. Now, in terms of pressure, does the 5-liter container have any connotation to the math at all? If these were moles, would it? Yes. Okay, if it were moles, it would. But since it's ATMs, we don't even worry about it. So, are mixed in the flask. And then this is the question. Calculate the equilibrium pressures. So what are they asking us to solve for? EF. They're asking us to calculate the EF values. You agree? Now, it says all of these things are mixed in a 5-liter flask. So if I come back to my rice table, where do all 3 of those numbers get plugged in? Initial, at the I row. You with me? So somebody help me out with the numbers. What was H2's value? 0.01. What was I2? Is it 0.005? And then H2 was 0.5. Okay, 0.5. Now, do you agree that all these are ATMs? No, but I just do it just for emphasis. Alright, now, remember, what do we do change in terms of? We do it in terms of X, right? But what matters in the X row? Coefficients. Now, do not write minus X plus X yet, because if you've done it, you're going to have to erase it. If you have out your how and when to use rice table sheets, which one would we use? The first question is, the first statement, if any of your initial values are 0, is that statement true? No. Your second statement is if any of your initial values are 0 and you don't have an EF value. Is that true? The last one is if none of your initial values are 0. Is that true? Yes. In that case, none are 0. Solve for Q. Compare to K. If none are 0, solve for Q, compare to K. Take these numbers and plug them into the K that you just wrote. Cool with that? So it's 0.05. They did. It's 100. We're solving for what? Q. Is it 01? Somebody run that calculation real quick. That should be real easy. Do 0.25 divided by those other two. Because what's 0.5 squared? 0.25. So you didn't have to square in the calculator. Just do 0.25 divided by 0.01 divided by point. So again, this is going to be Q, that QP that we're solving for. I think it's like 1,500 maybe. This is going to be QP we're solving for. Let me go back and show you. When none of your initial values are 0, solve for Q compared to K. Remember, in terms of how K and Q look, do they look any different? No. 5,000? Alright, so Q is 5,000. Just write down Q equals 5,000. I'm going to change pages, and I want you to write this down. So, in terms of K and Q, what was K again? 100. You guys tell me, where does my sign go? Say it alphabetically. Do you see a problem here? According to our point now, who's it pointing to? The reactants. So, are we at equilibrium? How would we know if we were at equilibrium? K would be equal to Q. That's not true. We've been spinning around on that. As dumb as that sounds, let it guide you there. That's real. I can explain the math like I did yesterday, or you can just know whatever way it's pointing, that's the way it's going to shift to. Cool with that? That's all you have to know. So, in order for us to go to the reactants, this point's telling me I need to make more reactants, right? So what has to happen to my products to make more reactants? I've got to lose some product, right? So when I go to my rice table, how do I normally have my signs for my change row? Reactants are normally negative. But in this case, what are they now? They're now positive. It's different. So, this goes back to the very first day I taught you rice tables. The terminology that I used, I said, in most reactions, the reactants are negative, the products are positive. What was the adjective I used? Most. What adjective did I not use? All. For this example right here. This is the reason why you can't say that anymore. Because in the case when K is less than Q, what do we have to make more of? We need more reactants. Well, if you need more reactants, the only way you can do them is make them positive, right? That's the only thing you can do. Now, remember, we do it in terms of X, correct? So it's X, but what matters in this one? Coefficients. Do you agree that would be true? So plus X minus 2X. And again, if you're still kind of like, where did this 2 come from? It came from right there. That yellow highlighter. What is the only thing we use the EX row for? Just bring our numbers down, helps us out a little bit. So that's the wrong button. So 0.01 plus X, 0.005 plus X, and 0.5 minus 2X. Great question. That's where we got to go next. In that maroon brown color that I just wrote, what is the answer to that question? Is there an EF? Actually, that's actually a bad way to say it. Is there an EF? No. No EF? So yes. Yep. We did this yesterday. did this yesterday, twice. No EF, plug EX into K and solve for X. Yesterday it was really easy. Let me show you. Remember yesterday we did, what was it, 115 or something, or 105 equals 1 plus x squared over 1 minus x squared. Remember all we did was take the square root of both sides and blah, 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 blah. So today, this is the one that's going to get us. But there's a huge bright light at the end of the tunnel. Do you agree? Do you agree that's true? I took products of EX over reactants of EX. If you were sitting in Miss Fold's class, or Miss Jeff Code or Mr. Johnson, I didn't say that out loud. Hello. I know. Okay. Could you solve for this? I couldn't either. You don't know why? Guess what you would have to have? What do we know about AP Chemistry in this thing? You don't have to do it. Okay? You could, but you still have to have the quadratic in the end. Because here's what it turns into. It's like 96x squared minus like 32x plus like point something. It's ridiculous. It's absurd is what it is. So, you don't have to do this. So, what was the whole purpose of me showing you this entire problem? Number one is to show you if for some reason you come up with a problem and you have to use the quadratic formula, you've screwed up. Formula. Okay. Number two, what I wanted you to see. What? No, this is right. There's two reasons that we read to this problem. Number one was if you get no zeros in your I row, what do? Solve for Q compared to K. That was the reason we did this. Okay? What was that? It's true. But what if it was? Who's Miss McGlon? Okay. So, I want to make an emphasis. Why did we do this problem? The first thing was, if none of the I row is a zero, none are zeros, solve for Q, and I cut it off, but compare to what? Compare it to K. When we compare, if K is less than Q, what happens in the change row? More reactants. We need the reactants positive. Let's play with this. What if K was greater than Q? Where would your signs be? Positive products, negative reactants, right? Just like normal. That was the first reason we showed this. Once we get down here, if you have no EF, what must you do? Plug it into K and solve for X, just like we did yesterday. The entire EF row, which is exactly what I did right here. So, Bryce, if you look back at that Rice table, this was the product. These two things are the reactants. You had the Rice table set up, don't you? Okay. So just take the products. Now, let me ask you something. This is important. Why in the world is the top thing squared? The coefficient. You just plug it right into K. That's where people mess up every year is they forget to add the coefficients again. You're done. We're not finishing the problem. You wouldn't. No, there will be no such thing as doing the quadratic formula on the test. They will not give you one that has it. If you end up with that, then you messed up. That should be a signal, wait a minute, this isn't right. I need to redo this. Something's wrong. Right? So that's an indicator of you that I'm never supposed to do the quadratic formula on this test at all. Don't put yourself in that situation. Okay. No, you can have one like that. It just may not force you into the quadratic. Basically, when you start foiling it out, you'll see that you have x squared plus or minus x plus or minus a value. All right, totally shifting gears. A trinomial, thank you. If you have a trinomial, are you with me on that? If I say you better be. I think some of you are like. Totally shifting gears. We're finally getting into Le Chatelier, and it's going to make a whole lot more sense now because you actually understand what I mean by shifts. Le Chatelier's principle can be stated as follows. A change in one of the variables, and I want you to highlight or circle this word, that momentarily. What does momentarily mean? For a split amount of time. It can be for a few seconds, it can be for a few nanoseconds, it can be up to possibly even a minute. But it's momentary, which means, is it always going to be that way? No, because a reaction at equilibrium will always return to equilibrium. If you spin around on a bat, will you always stay dizzy? Eventually, your body gets back in equilibrium. Okay? So, momentary. Le Chatelier's principle will change in one of the variables that momentarily takes it away from equilibrium. Spinning around on a bat, doing something to make it change. And the system produces this is the word that makes everybody's head hurt. Shift. Why they picked that term, I don't know. But what's happening is the reaction is doing something that opposes the effect. So, shift in the position of the equilibrium that counteracts. What does counteract mean? Opposes the action, right? So basically, it does the opposite. So it's going to do something to make everything work again. That effect of this change. There are three ways in which we can change the condition of equilibrium. The first thing you can do is changing the concentration. Now, I want you to add this word above it. It's not just a concentration we work with all the time. What's the other unit we work with? Very good. There's one of two ways you can change the concentration and pressure. What are the only two ways? What's wrong? Good point. We'll talk about that in a minute. Okay. No, you're right. Okay. So, changing the concentration. We can either add something or we can take something away. That's it. You can either put it in or you can take it out. Those are the only ways. Now, how do you shift from an addition? Away? How do you shift from a takeaway? Towards, right? You with me? What's wrong? It's a bad misspell. It's supposed to be volume. You're the first person to catch that. Changing the pressure / volume on the system. I want you to do this. Now, what is the only state of matter that causes a pressure? A gas. So the changing in the pressure or volume only depends upon the moles of a gas. Moles of a gas. Yes? Moles of a gas. So let's pretend that all of a sudden you guys are molecules for a second. And you are running around in this room at a slow jog. Now, you are not human anymore. You are an object. If you begin running at a constant velocity in a certain direction, will your direction deviate on its own? Physics people? If you are running at a constant velocity in a certain direction, will your direction change on its own? No. What is the only thing that can alter your direction? A force. Now, if you're running and all of a sudden you run into something, will that change your direction? If you run into one another, it will change. If you run into the wall, it will change. Correct? Let's pretend that we're ideal gases. Listen. so difficult to talk to sometimes. If you run into the wall in an ideal gas, would you return at the same velocity? Yes, because ideal gases have what's called elastic collisions. What is an elastic collision? Whatever energy is put in comes out at the same amount. That's like playing wall ball. When you throw the ball at the wall, it comes back at the same velocity you threw it at. We know in real life that doesn't happen. That's why I said ideal. None of you are ideal. Okay? So, if you were to start running at a constant velocity, if I left your speed the same and took you and forced you into that office in there, what happened to the volume? The volume decreased, so what would happen to your collisions? What would happen to your pressure? It would increase. So how are pressure and volume related? Inversely, or indirectly. When one goes up, the other goes down. Let's pretend I started you in the office and then brought you out here. What's going to happen to your collisions? They're going to go down, so your pressure also goes down. That's how pressure and volume works. So you may want to jot that note down. Pressure, volume, indirectly or inversely related. And the last one, changing of the temperature. If you're on the iPad, add a new page. If you're on notes, you're going to have to add this. Okay? If we're talking about a change in temperature, you have to know the answer to that question. Is it endothermic or is it exothermic? Now, if you look at a reaction, there's only one way to tell if it's endo or exo. What is that one thing? No. That's thermodynamically favorable. There's one variable that tells you exo or endo. Delta H. Well done, Matt. If it's endo, what is the sign of delta H? Positive delta H means it's endo. This is the important thing. If it's endothermic, where's the heat in the reaction? Heat is the reactant. So, when you write, and I'm going to just write this in brown, when you write A is in equilibrium with B, if it's an endothermic reaction, how would you write heat? Heat plus A, very good. That's endothermic. Now, can a reaction be both? Parts of it can, but the whole thing can't. The whole thing has to be one. There's some of each one. If it's exo, what is the sign of delta H? Negative. We have exothermic. Heat is a what? How would you know that? Because exothermic means exiting. It means releasing. So, if I were to write it in red and it were exothermic, how would you write this reaction if it were exothermic? A yields B plus heat. Okay? Now, once you know this, then it's just, is it going, are you adding heat or are you taking away heat? And you shift back and forth based on addition or subtraction. Works the same way. But the key is, if you don't know this, you can't do temperature change. Bottom line. And I had two cool little videos, but the technology is in here is going to allow me to do it. So again, we'll work on that in a minute. So, Chatelier's principle. Again, three ways. If a stress is applied to a system at equilibrium, the position of the equilibrium will shift in the direction which reduces the stress. So if I add something, what's going to happen to the stress? It's going to shift to get rid of the addition, right? If I take something out, what's it going to do? It's going to shift to recover that. Does that make sense? Okay. Shift occurs to reestablish equilibrium. Think about it. Generally, it's products over reactants. K always wants to be constant, right? We want it to be the same. Adding or removing a reagent causes the equilibrium to shift to reestablish K. As long as you milk a cow, guess what she keeps doing? She keeps making milk. If you stop milking a cow, guess what happens? She dries up. Okay? Increasing pressure. This is the big one. Everybody always misses this one. Put a big star beside that bullet right there. Increasing pressure causes the equilibrium to shift to what? The fewest moles. So if we go up in pressure, we go to the fewest moles. Everyone misses that every year. Now let me ask you something. How in the world do you know the number of moles of a gas? Count the coefficients. Count them. But you're only counting the coefficients of what? Of a gas. Nothing else. Just the gas. Yes, sir. Alex, you just told me this right here, right? Finish it. Products minus reactants. Of what? Gases. Yes? Fill it in. Try again. Filled it in. So, but here's my question. If I increase my pressure, how do you shift from an increase in pressure to the fewest moles? What's my total number of moles on the left-hand side? What's my total number of moles on the right-hand side? 2. So if I increase my pressure, what way am I shifting? Why? To the products. Because it's the fewest moles of a gas. That's how you do it. Every year, students miss that problem the most because they don't pay attention to the shifting of the pressures. Okay? That's why we got to practice this. Monday, we're going to practice with Charlotte. Okay? This is a big one as well. So if you're highlighting, change the highlighter color. And they try to get students on this one every year. If I add a catalyst, how does it affect my equilibrium? It doesn't. What does it make it do? Get there faster. It has no effect on the equilibrium. It affects baby K. Adding a catalyst to a reaction causes no shift and has no effect on K. It just causes equilibrium to be established faster. Hint, hint, wink, wink. I can't say that any louder to you. Did you get that, Fuller? Glad. What if they said, I add neon gas to the reaction? What in the heck is neon gas? What kind of gas? It's a noble gas. Which is what? What does inert mean? How can it affect equilibrium if it doesn't react? It doesn't. Just throwing that at you. Just throwing that at you. Oops, wrong way. Because it's a noble gas. Oh, yeah, that's why they're noble. 2 minutes. Last question. For the reaction, listen, please, guys. For the reaction 2AB in equilibrium with 2A plus B. Matter of fact, guys, this is supposed to be a low 2, not a, or is it? Nope. It is supposed to be in front of. It's supposed to be in front of. The delta H is positive 26. As soon as you see that, what do you know? Y endo. Very good. So where do we add heat? Yay? The dark line going down, products or reactants? Those are my reactants, which is what? Yes? Once we have established right here, once that line flatlines, what are we at? True? Now, all of a sudden, there's a huge jump in this thing. What stress has occurred in this system? Label the graph with what is happening at each stage. Do you agree that we've added equilibrium right here too? Oh, hold on. Whoa. Notice what it says right here. Please listen. It says forward and reverse. So what we're only working with is we're working with reactants only. What would cause the reactants to skyrocket? No. We add the reactant. Because you notice what it says. It's the rate. Jacks up and then it decreases back down. Okay? That's the only way we had to add a reactant to make that happen.